Well, it's good to be back here at the Interlligent UK RF and Microwave Seminar. As Helen says, I'm going to be talking about 5G components and technologies, that's specifically millimeter wave 5G. So the full details of the 5G specification are yet to be defined. But we do know that 5G is planned to allow much higher data rates. Extremely low latencies, we touched on this earlier, less than 1 millisecond. Uniform coverage over a wide area network. And it's also intended to encourage the development of new applications. And it absolutely will. I remember when 3G was being developed and people were saying, oh, what's the killer app? What are we going to be using all this data capacity for? Nobody's doing that now. They're just banging their phones wishing they had an LTE connection instead of this rubbish 3G connection. As soon as the wireless data capacity is there, people will find a way to use it. 5G will require huge tranches of contiguous spectrum. And this is why millimeter wave is one of the key components of 5G. Until quite recently, people would have said, non-line of sight millimeter wave communications, are you mad? But there's been a lot of research been done in urban environments, and there are ways to address these issues, and it has been demonstrated that the problems can be overcome. So, in this presentation, I'm going to be discussing the likely operating bands. And I have no axe to grind here. We're an independent design consultancy. I'll be telling you what I think the bands will be. The options for the realisation of millimeter wave components. Some examples of the packaging technologies that are being used. Examples of millimeter wave components that we at Plextek RFI have designed for 5G demonstrator systems. So, the likely operating bands. These are listed here, and they're listed in the order I believe that you will see the deployment of millimeter wave 5G. Top of the list, you've got the 28 gigahertz band. That's an FCC license band. The FCC recently surprised a lot of people by stealing a mark on the rest of the world, really, and announcing about 7 gigahertz of spectrum available for 5G. Then we've got the 39 gigahertz FCC license band, just below that a 37. Now, recently announced, and it was mentioned earlier, this pioneer band, the EU's Radio Spectrum Policy Group announced 24.25 to 27.5 gigahertz. It's sort of all well and good announcing a band, but you have to tell the people who are developing the equipment that this band exists. So at the moment, there's actually not a huge amount of stuff available in this band, but it will start to become available. They also mentioned the 32 gigahertz band, the 31.8 to 33.4, as also an attractive band, and the 42 gigahertz band, 40.5 to 43.5, as a longer term option. Now, all of these bands are all in Ka band, and or thereabouts. I firmly believe this is where we're going to see millimeter wave 5G deployed, and I think it's going to be roughly in this order. And this is based on the work people have paid us to do, and also the inquiries we've had for millimeter wave 5G. So, just got a little summary slide here looking at the sort of technologies that people are using and will use for the millimeter wave blocks. Now, for the PA, I've got PHEMT here. PHEMTs are actually a great technology for millimeter wave PAs. And if you try and buy a millimeter wave PA, odds are you'll probably end up buying a PHEMT part. And that's because they offer very good linearity, offer modest supply voltage. I've put GaN question mark. Everybody who has a GaN process tells me that GaN is going to be key for 5G. I'm perfectly happy to believe people might use GaN in 5G applications, but GaN has a very high power density, but it normally requires quite a high supply voltage because it has a high knee voltage, about 5 volts. Now, I happen to know that there are people working on new innovative GaN processes that will bring this knee voltage down. But for the time being, GaN requires quite a high operating voltage. So I'm not sure it's really going to be that big a player in the mobile terminals. The base stations, it depends how they do them. In honesty, I can see the 5G base stations being very similar to the user terminals. So LNAs, PHEMTs make great LNAs, but you can also do a good LNA in SiGe, particularly if you manage to integrate the LNA into more highly integrated receiver. Transmit-receive switches, pin diodes actually make great transmit-receive switches. You can do TR switches in PHEMT and silicon and insulator at these frequencies. The problem is that the isolation you can get is limited. A PHEMT structure is like this with source and drain fingers. As all FET structures are like this, they have a lot of residual capacitance that you can't get rid of. So as you try to get enough isolation, you end up making the transistor in the switch increasingly small, which means that the losses go up and the linearity comes down. There are things you can do, and we have done these things, but if you want high linearity and a high power handling, a pin diode switch is a good way to go. Up converters and down converters, all these will come to play. PHEMT, I know that PHEMT will come to play because we're developing such things for people today. SiGe and CMOS will also be the people are releasing 5G components or components badged as 5G in CMOS. I think ultimately, as we move down towards the more fully integrated transceivers, as 5G matures, I'm absolutely convinced the highly integrated transceivers will be in SiGe or CMOS. Possibly silicon and insulator. I know people, mainly people with vested interest in silicon and insulator, are developing components in that technology. So packaging options now. Pretty much all millimeter wave ICs that sell in sensible volumes come in some form of SMT package. Now, I've listed a number of packaging options. Overmolded plastic. Now this is where you put the IC down on a lead frame, you bond it up with wire bonds, and you put a blob of plastic on top. A little bit more sophisticated than that, but that's broadly how it is. Now, these frequency limits, they're not hard and fast. I'm not saying you can't go to 31 gigahertz in this, but roughly up to about 30 gigahertz, you can get nice performance from an overmolded plastic. Normally use a custom lead frame. Certainly everything we've done above 20 gigahertz and got good performance, we've used a custom lead frame. Air cavity plastic, we've used up to about 42, 43 gigahertz. And I've got examples of most of these packaging technologies to show you, real world examples, components that have been made and developed, and some of them used in systems. Laminate. With laminate packaging, this is a custom laminate package, you can actually get slightly shorter bond wire than you can with the air cavity or overmolded plastic. You can configure it so that your substrate is about the same level as the die. So that allows you to push it a little bit more. I put 45 gigahertz. I'm not saying you couldn't do a 46 gigahertz components, but thereabouts. They're multi-chip modules. And you can realize multi-chip modules working up to 100 gigahertz. Mike Geen of Filtronic will be speaking next. He'll be talking about some E-band transceivers that they do. And they use Burr die in some form of multi-chip module. It gets rid of the packaging parasitics and it allows you to push frequency still further. So I've got a few slides just showing you, the next few slides are just to illustrate the packaging technologies. This is a 28 gigahertz application that we've done for one of our clients on a commercially available gas foundry. This is in an overmolded plastic package, packaged by a volume manufacturer, uses a custom lead frame. It's got low noise amplification, power amplification, and switching inside it. This is an air cavity package. This is a 39 gigahertz PA. Here's a little image of what's inside of it. And all millimeter wave PAs look like this. All the ones that work anyway. You have an array of transistors at the output, and you power combine them, sort of like the manifold of a V8 car. And the reason you do it, if you made one big transistor, it wouldn't have any gain. So you make a transistor as big as you can get away with, so it's still got gain, but a decent amount of output power. And you combine them. And you can see it's got, well, maybe you can't see, but it's got a little coupler there to do power detection. It's got 1, 2, 3, 4 stages of amplification. And this is its package. It looks like a standard overmolded package, but it's an air cavity package. So you sort of imagine you build up these walls around it, then you glue a plastic lid on. But to look at, you wouldn't notice any difference from the overmolded. This is a little PCB we did it on. This is a Rogers 4003, 8 thou thick. We configure it to use edge-mounted connectors. That's just a little aluminium carrier that it's on for rigidity and also for thermal reasons. This slide shows a laminate packaging technology. The stuff in this photograph is nothing to do with 5G. It's just a nice photograph that allows you to see how the technology works. And you have a bunch of lids fabricated in the same substrate as a bunch of package bases, and you can put the die essentially inside a well, bond it to the laminate, and it works great. And this is genuinely a 5G component. We designed the custom package. The die was designed by our client. And this has been shipped in tens of thousands. And remember, 5G doesn't exist yet. So, a millimeter wave. In the interest of full disclosure, these actually aren't ICs that are used in 5G. But they are millimeter wave ICs that we've designed. In this case here, you can see they're just mounted on the surface of a Duroid substrate. You can see you've got a printed coupler here. Now, you've got two options really with your wire bond. You can probably just make out here, this is what we call a V-bond. So you use multiple bond wires to reduce the inductance. But if you put them in perfect parallel, then you get a mutual inductance, which has the effect of negating some of that benefit. So we use what we call a V-bond, so they go a little bit like that. The other thing you can do is use tapes. And this is two E-band ICs we designed, and you can see here there are 3 tape bonds across, connecting both the grounds of the ground signal ground and the signal path. So a few examples of millimeter wave components that we've designed. The first is that 39 gigahertz PA I showed you, the air cavity package. Just a little photograph of it up here to remind you. This is the S parameters of 3 different units. You can see you've got about 20 dB of gain. And then what we look at is the IP3 against frequency. Now, all of the 5G systems will require a degree of linearity. And this has round about 40 dBm IP3 across the band, which I think is as good as anything you can buy. And this is an SMT package on a PCB. So what we do is we mount that on there. We also develop some TRL calibration structures. So we calibrate up to these reference planes. So we measure the PA on the PCB, including the effects of the PCB, because you have to have a PCB. There's no point measuring these things floating in free space. This one is a 28 gigahertz SP40. This is fabricated on Win Semiconductor's pin diode process. It's just about released. We had some advanced access to it because we have a good relationship with them. And you can see that we get a loss here around about 1 dB. Nice matches. And just going back, so the benefits of the PIN diode, it's a vertical structure, PIN, and you end up with a lot lower capacitance. The other thing we've done here is we've got a shunt only design, which helps us keep the losses down. So that's why we're around about 1 dB. This is a 28 gigahertz PA with an integral 4-bit phase shifter. Now, earlier Chris was talking about phase shifters. This is a 4-bit design. Often, you know, for this sort of beam steaming we're envisaging on 5G, 4-bit will be plenty. We've got an input stage here. This little thing here is a gain slope compensation network to help flatten the gain versus frequency response. 2 devices here, 4 devices at the output. And this is the phase shift versus frequency. All reasonably flat. RMS phase error of about 2 degrees. And this shows the S21 across all states and frequency. Now, the way these phase shifters work, they're switched high-pass, low-pass filters. You always get a degree of amplitude variation with phase state. The key is to try and minimize that during the design process. So you can see this is quite modest. I think it's about plus or minus 0.8. And the return losses, you always get a large degree of variation in return loss because you're changing the phase all the time. So all the reflected waves are adding with the incident waves differently. So you always get a large variation. The key is to keep the worst case pretty low. And this just shows the output power, which is about a watt, and the IP3 about 38, 39 dBm. So this is something new we've just done since the Radio Spectrum Policy Group surprised us with this 26 gigahertz Pioneer band and this 32 gigahertz band. It's becoming increasingly obvious to us that there isn't going to be a universal allocation that you can use 1 millimeter wave 5G frequency across the world. It's just not going to happen. So we can see some benefits in having dual band components. That's pretty difficult at RF. It starts getting really difficult when you're up at millimeter waves. But we've done this PA anyway, which covers these bands. You can see the 4 transistors at the output. There are lots of other transistors dotted around, and these are doing the switching of the components to change between the 2 bands. The difficulty you've got is that they're not really switches, because if you look at the off case, you don't have a load of isolation, you have a capacitor. So they're really switchable reactances. So the difficulty is to design the PA so it works with all of these parasitics. There's an article which has been published in the May issue of Microwaves and RF. You can view it online. You can probably get a link to it from the press page of our website. But if you want to read more about that, it describes the design process in a little more detail. I've just got a couple of plots. You can see here, the red plot's the 26 gigahertz band. The blue plot is the 32 gig. And you can see the shift in the gain response there, shift in the output match. The input match is pretty good across the full band. And that is, again, we've used one of these gain compensation networks at the input. So what this does is it puts more loss at the lower part of the band, less at the higher part of the band. It also means that you tend to get a pretty good input match. And here you can see the P1 dB and the efficiency as you switch between the bands. So just over a watt at the 26 gig band, and just about a watt at the 32 gig. And you can see the PAE. Now you do pay a little bit on PAE for having a band switchable design, but it's still pretty reasonable. 30% here, about 27% here. And the thing with components for wireless applications is what's important is that they're good enough and they cost as little as you can get away with. So we think, you know, in the fullness of time, this sort of dual band approach could pay real dividends. Ultimately, hard as it may seem to believe, we'll have 5G, millimeter wave 5G products. There are multi-band millimeter wave 5G products. So, a few conclusions. 5G will use millimeter wave line of sight links. Sorry, non-line of sight links. A lot of work is underway at the moment. A lot of work. All of the big companies are pumping loads of money into these developments. And they're all developing kit targeting the millimeter wave 5G bands. And I've told you what I think are the most likely ones. We can expect innovative component solutions, innovative packaging technologies. Operating bands still to be confirmed. Ka band is what we believe is going to be there, but there won't be a single band worldwide. Dual band components could become very attractive. That's just to remind me that I've finished speaking. I'd be happy to try and answer any questions anyone may have.
Chris?
Yeah, thanks, Lee. In the early part of your presentation, we were talking about different technologies, and of course the inclination of the transceiver, the silicon transceiver maker, will be to try to put everything, including the front end, onto the actual transceiver, a bit like YG has sort of got that direction. 5G is a bit different because potentially the power levels are higher. Do you have a sort of feel yourself in terms of what type of power levels per chain would be required in order to make a differentiation between gas and GaN and silicon?
Good question. So you showed some power levels earlier, and I think you were saying handset PAs of about the 23 dBm level transmitted, so a little bit backed off. And those are broadly in line with the things we're developing. There is also a market for the base station side of things where people are looking at architectures which require slightly more power, so the 1 watt level. I know people are developing silicon PAs at the sort of 28 gigahertz band. In honesty, it's quite a challenge to get above 20 dBm of saturated power. So I think they're going to struggle. I mean, we shouldn't forget that CMOS PAs for the 2 and 3G cellular have been available for some time, but everybody's still using gas because it gives you quite a lot better linearity. And in honesty, it needn't be super expensive. It's a mature technology. It could be the GaN is more, roughly speaking, GaN per unit area is currently about twice as expensive as pHEMT, but it has got a higher power density. So if you need that higher power density, if you've got a GaN technology that will do your frequency range and you have the higher supply voltage, then you may move that way. But at the moment, all of the PAs we're doing are all in pHEMT. For 5G, that is. We're doing lots of GaN PAs for other things.
Hi there.
Hi, Harry.
The dual band PA was already very impressive, but I'm just wondering, because I'm anticipating questions from people who look at it, do you think it's also possible to do that as a Doherty at some stage?
Well, that's an interesting question. I think I'd like to do the Doherty integrated PA first, then think about doing the dual band one. But Doherty PA with digital pre-distortion, it works quite well. A Doherty PA will occupy more die area. So I think people will go that way if they need to, but if they can get away without it, that's what they'll use. And they'll do things as simply and as cheaply as they can get away with.
Yeah, so it depends on the PAPR really.
Yeah.
Just a quick question.
Yeah.
You mentioned wire bonds.
Yeah.
I was surprised. Not FlipChip?
No. Good Lord, no. So people mistakenly think FlipChip is the panacea. It's not. It's not. You open up any millimeter wave module, open up Mike's 70 gigahertz millimeter wave module, 76 to 86 gig. You can't because he won't let you. He won't even show you it. But there are no FlipChip components in there. All these millimeter wave ICs are down flat, and they'll either use a V-bond or a tape bond. So why? Well, the flip chip only gets away one problem. It reduces the bond inductance, but it gives you a whole load more problems. You've got all of this millimeter wave circuitry then in close proximity with a substrate. Where are your grounds now? Your grounds to your PCB on the back side of your PCB. Your grounds to your MMIC are on the top side there. Where's your heat sink? What do? You put a little heat sink on top of your IC? So there are lots of difficulties. Now at the lower frequencies, people get around these problems. And what they do, for example, front-end modules for your 3G phone, they'll have a PA which is flip-chipped. And they do it not for the bond wire inductors because it keeps the size down. And what they have is a technology where they have little bumps on all of the emitter fingers of the transistors, because they're all in gap HBT PAs. They have little bumps on those, and those contact to the module itself, and they suck the heat out that way.
What about EWLB, like Infineon packaging?
Yeah, so that's an interesting one, and that so this is a wafer level chip scale packaging. Now, Infineon use this. Infineon don't have through substrate vias, so they had to think of another way. So what they do is they flip it onto what they call this wafer level chip scale packaging, and that essentially allows them to have their own via, because they then have vias coming through that way. So they're finding an alternative way to get the low inductance ground vias without having a via through the silicon, which is pretty difficult to do.
So maybe that could be something that's
So you could do that, absolutely. And to be honest with you, I think any millimeter wave silicon ICs will probably use something like that. The other option you've got with a silicon IC to get around the problem if you don't do that is you've got to find a low inductance grounding methodology. And at lower frequencies, you can do loads and loads of ground bonds. But as you go up in frequency, even that amount of inductance is too much. So you can either use differential circuitry throughout, which is very popular in the silicon world, or you can find a way of doing some flip chip, or a combination of both.
Okay, thank you ever
Thanks.
so much.